Good day. Here is another live session for mathematics. Now, for today's session, we are going to be looking at a lot of interesting topics. Of course, for our first session, we have already looked at concepts like indices, logarithms, and talked about the laws that affect them. Not just the laws that affect them, but how to also apply those laws, right? We looked at the concept of indices being categorized with values of variables in this form, where there is a base and there is a power. We have looked at this in detail. We also considered various laws that affect them, whether it's the multiplication, the division, the power multiplication, or the fractional law. Regardless of any of these laws, we have also looked at various ways in which we can use all of this. You can find all of this and more on our platform. You just have to log into www.yourstudypad.com to practice on this and see how we applied this. From indices, we also looked at logarithms, and we considered values of variables that look like this, where there is a number and there is a base of operation. And then we also considered various laws in which we could use within this concept, from the concept of addition, when the base is the same, to the concept of subtraction, when the base is the same as well, to different other kinds of concepts that we also looked at. Now, of course, you can also find more on this from our platform. Now that we have looked at this, for today, we are going to be looking at numbers themselves. Of course, we have talked about indices as a representation of numbers in smaller forms. Of course, you can represent 8 as 2 raised to the power 3. You can represent 16 as 2 raised to the power 4, or as 4 raised to the power 2, and so on and so forth. Logarithm also takes representation of numbers. You can represent 3 as the logarithm of 8 to base 2. You can represent 4 as the logarithm of 16 to base 2, and so on and so forth, right? However, for today, we are going to be beginning the session today with how we can express numbers in terms of their equivalent classes. How we can express numbers in terms of their equivalent classes. That is going to be our focus for this class. To that end, we will be beginning the concept of modular arithmetic. This is in fact one of the simplest concepts you are going to come across as far as mathematics is concerned. However, it's also the concept that has one of the widest range of applications in real life. And because of this, questions tend to swarm around this concept. So it's very, very important for us to understand how to deal with it. Now, for modular arithmetic, what are the key concepts that exist? First off is the fact that we are going to be using what we call a remainder. For that remainder, we are going to be needing to find the equivalent form of that remainder when we divide a number by another number in this form, A mod n. So we need forms R equivalent to A mod n. Now, what does this mathematical statement mean in plain English? What this simply means is that R is the equivalent value obtained when A is divided or is divided by a number n. So which means that equivalent value is obtained whenever a is divided by n. Now let's put more context to this. We know that we are saying that a must be divided by a number n. That is the very first line. So how do we put that? If we divide a by n, we know that first and foremost we will have a quotient. What do we call a quotient? A quotient is the whole number part of our division. Do not forget, for instance, if you have 7 divided by 2, you first and foremost will say you have 3 whole number 1 over 2. 3 whole number 1 over 2. This is like conversion from improper fraction to mixed fraction. This is something you are already very familiar with. Improper fraction to mixed fraction. So you have 7 divided by 2. You have 2 will go in 7 3 times, remainder 1. So it means that the quotient in this case is 3, and then you have a remainder of 1, which in this case we are calling half. So it means that when we deal with modular arithmetic, we are most concerned with the remainders. That remainder is simply the equivalent value we obtain whenever a number is divided by another number. Now, how important is this value? We are going to be looking at it in detail. Do not forget that this number we are using to divide is what we call the modulo value. We call it the modulo value. Why? Because this number is very, very important, such that with this modulo value, the term of the remainder will change with respect to whatever this modulo value is. For instance, just as you have 7 divided by 2, where the remainder in this case is 1, if you were to take 7 divided by 3, you would have what? 2 whole number 1 over 3. What do you see? The remainder in this case is still 1. However, what happens when you take 7 divided by 4? In this case, you simply have 3 divided by 4, because in essence, you would have 1 whole number 3 over 4, which means that 4 will divide 7 completely just once, and then you would have a remainder of 3. What does this tell you? It means that even though you are using that same number, that modulo value determines what the remainder will be. And all these remainders will be valid within the concept of that modulo value. This is what makes modular arithmetic very, very important. So our key takeaway is this. Number 1, the modulo value changes the sigma form or the standard form of the remainder. 2, the remainder is the equivalent value obtained whenever we divide a number by that modulo value or by another number, where that other number is the modulo value, right? And then that remainder is, of course, the equivalent value, and of course, the most important, simplest representation of the big number. Now, let's look at examples. Of course, in practice, how do you carry out modular arithmetic? The easiest way of carrying out modular arithmetic is through the use of the long division. If you can perfect the use of the long division, which I know you have already practiced a lot at this point, then you would have no problem with modular arithmetic. Let's put it into practice. What will be, so let's have an example. What will be the equivalent form of 15 mod 4? So let's find x if x is equivalent to 15 mod 4. How do we do this? We must identify 15 as our number, and then we must identify 4 as our modulo value. And then what we proceed to do is to express this in long division. The modulo value comes outside, the number goes inside. Simple. Now, the same way we do long division. 1 divided by 4, obviously, at this level is impossible. So it means that what you do is you add up or you join it with the next number. So you now have 15. 15 divided by 4, you can take out 4 in 15 3 whole times. So you'd have 3. And then you do 3 times 4 gives you 12. And then at this point, you subtract. So 15 minus 12 gives you 3. 3 divided by 4 can't work anymore. So at the point where you can no longer completely remove that modulo value from what you have here, you have gotten your remainder. Of course, whatever is on top here is your quotient. But then in modular arithmetic, we have no need for the quotient value. What we need is the remainder value, right? So here, the remainder is 3. What this means is that x is equal to 3, which obviously follows that 3 is equivalent to 15 mod 4. End of that question. Let's take another one. What if we want to find, so let's call this 1, 2, let us find x if x is equivalent to 101 mod 3. Of course, x is just a letter. We can just say if you don't like x, you can always say find y. That will still not change anything. That's not a problem. Again, you identify this as your number. Then you identify this as your modulo value. And then you proceed towards long division. 3 comes outside, 101 goes inside. 3 dividing 1 is practically impossible. So you join the next number. 3 can divide 10. And then you have 3 whole times. 3 times 3 gives you 9. So you subtract. 10 minus 9 gives you 1. Bring this last number down. So you have 11. That's how long division works. You pick the first value. If the first value cannot divide what is outside, or cannot be divided by what is outside, you add the next value to it. Use the outside number to divide it. Get your quotient, multiply, then subtract by that component. 10 minus 9 gives you 1. So this number left, just bring it down. You now have 11 here. And then you do 11 divided by 3. That gives you 3 again, right? Obviously, because 1 divided by 3 would not work, so you have to bring that number down. That's why you have 11 here. 11 divided by 3 gives you 3. And then 3 times 3 gives you 9, which means 11 minus 9 is 2. 2 divided by 3 would not work, but there is no other number to bring down anymore. So it means that 2 is your remainder. Are we together? 2 is your remainder. Of course, this means that y is equal to 2. Of course, that means that 2 is equivalent to 101 mod 3. So 2 is the equivalent value you get when 101 is divided by 3. This is how modular arithmetic works. It is not a lot of big deal. The major thing is using your long divisions clearly. Long division deals with divisions digits by digits, right? Let's take, we have taken 3 digits now, 2 digits here. So you have seen how we take the numbers down. Let's take 3 digits and see what happens. Let's say we have find x, y, z if z is equivalent to, let's say 1024 mod 5, for instance. Or let's say mod 4. Let's start with that. Now, again, this is our number. This is our modulo value. So we begin our long division. Do not forget the modulo value comes outside. The number goes inside. Now, 1 cannot divide 4. So you join 1 with the next digit. 10 divided by 4, you get 2 whole number. So you have 2. 2 times 4 gives you 8. You subtract between these digits. Now you have 0 minus 8 is impossible, so you borrow 1 here. 10 minus 8 gives you 2. 2 divided by 4 will not work. So you bring the next digit down to meet it. Are we together? Now you do 22 divided by 4. That gives you 5 whole number. 5 times 4 gives you 20. Right? And then you subtract. 2 minus 0, you have 2. 2 minus 2, you have 0. So that goes. Now, 2 divided by 4 will not go. So you have to bring in the next digit. Now, in this case, there is a next digit, which is 4. Do you see? So we are bringing them down digit by digit. Not that you just bring all the numbers down at the same time. For long division, where you are doing it manually, you bring down digits by digits. I hope that's clear. So now you have 24 divided by 4 gives you 6. 6 times 4 gives you 24. You subtract 4 minus 4, 0. 2 minus 2, 0. So it means that in this case you have 0. 0 minus 4 obviously would not go as well. So, or you have 0, which in this case is insignificant. So it means that 0 is your remainder. Right? Yes, you can also have 0 as your remainder. What it simply means is that z is equal to 0, which follows that 0 is the equivalent value when 1024 is divided by 4. Simple. 0 is equivalent to 1024 modulo 4. This is what it means to carry out modular arithmetic. Simple and short. Now, we look at it that, oh, we are getting 0, we are getting 2, we are getting 3. What is that key thing that is familiar or that is bringing all these concepts together? The key thing that brings all these concepts together is that if you notice, none of the equivalent value we have gotten has ever been as much as the modulo value. Yes, your equivalent value you have gotten, or your remainder that you will get, will never be as much as the equivalent value. That is because the equivalent values, or the class of equivalent values, which is what we call equivalent classes, are always less than the modulo value itself. And it follows instinctively. If you look at this, where we have 7 divided by 2, you had 3 whole number, 1 over 2. Whenever you write your values in mixed fraction, you have never seen a mixed fraction, or you will never see a mixed fraction where the remainder here will be greater than this denominator, or will even be equal to this denominator. You will never find a case like that. Every time you express in mixed fractions, the numerator of here, which is also obviously the remainder, will always be less, strictly less, than this denominator. That is the same principle. That is why the equivalent values will always be less than the modulo value. You can try it for any kind of mixed fraction. If you have not taken note of it at this point in time, take note of it now. In any mixed fraction you'll find, the numerator of the fraction part will never be as much as the denominator of that fraction part, which goes to say that the remainder will never be as much as the divisor. So the modulo value is obviously also the divisor, and then that remainder is the numerator part, right? You can check it for any and every single mixed fraction you can find. Now that we have gotten the theory behind it, or the practice behind it, let's now write the theoretical or mathematical form for it, and then see what we can generate from that. Now, we have said one major thing. The numerator of the fractional part of a mixed fraction will never be as much as the denominator, or the remainder will never be as much as the divisor. It means that if n is the modulo class, then the equivalent classes, or we are saying the class of equivalent values, will never equal or be more than n. If n is a modulo class, then the class of equivalent values, which in fact are remainders, will never equal or be more than n. Now, this is very, very important because we are simply considering what 101 will be in this modulo value or in this modulo class, right? We need the equivalent form of 101 in mode 3. That is what we are simply doing in modular arithmetic. We are trying to convert a big number into that modulo class. And in fact, let us now look at what that modulo class looks like. So, if we are to consider the equivalent class of mode n, we will be talking about values starting from 0, 1, 2, up to n minus 1. So this set of values are the only values permitted in a modulo class of n. Let's put it into writing. It means that, for instance, if you have a modulo class of 4, then the only values permitted are 0, 1, 2, and 3, which gives us two rules. Number one, the equivalent values are always non-negative. I say non-negative because we do not completely classify whether 0 is positive or negative. However, it is a number that is devoid of any sign. You will not write something as mundane as plus 0 or minus 0. We just write it at 0. So it means that we can safely consider it as a non-negative number. So our goal is to ensure that we do not have values that carry a minus sign. Hence the reason why we say the equivalent values are always non-negative. That's one. Number two, the equivalent values are always less than the modulo class. So if we are in mode 4, the equivalent values are 0, 1, 2, and 3. 4 values because we are in mode 4. If you are in mode 5, you have 0, 1, 2, 3, and 4. 5 values. So the number of values in that equivalent class tallies with the modulo value itself. If you are in mode 10, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 values from 0 to 9. None of the values will be equal to 10 or greater than 10, and all of the values will be 10 in number. Now, how then does it mean when we now have something like 15 mode 4? This leads us to the reason why we have to carry out modular arithmetic. Because we now have 15 mode 4, and 15 is obviously a number bigger than 4, but it cannot exist in a modulo class of 4. So we need to be able to convert 15 into a number that is equivalent to 15, but in the modulo class of 4.